In this video we will be talking about panel data. Probably survey data is the most common type of data in statistics and political science, but my guess is that the next most common type of data is panel data. Data where typically we have countries, but it can also be provinces or parties or countries or etc. Over time, where we observe the same countries in different years. So the structure of this data set combines both time series, in the sense that we have the same observations for many time periods, and cross-sectional features, because in each time period we have a whole range of observations. So for example, every country in every year. And then we can collect data on each of those country-year combinations, for example GDP per capita, or population size, and so forth. And we will see later that we are here sort of assuming that many of these variables vary over time. Of course, we also have institutional variables or linkage variables about what was a colonial power, etc., that actually do not vary over time. And they have some special consideration later on. But the basic structure of panel data is country-year observation or unit time observation, and then data collected for each of those time periods for each of those units. So we need to change the notation a little bit. We have used I for units, and in the time series class we used T for indicating which time period. Now we have the combination, so you get the subscript IT to indicate a particular value for a particular unit at a particular time period. And this means that everything we have said in the time series class, everything we've said in the OLS class, and everything we've said in the multi-level modeling class all applies to panel data. So panel data is not easy to deal with because there's a lot of different considerations. The plus side is that this week's lecture is going to be relatively short because there's not that much added material. The downside is the actual data is fairly difficult to. Be very careful when you read about panel data, and I should actually say panel data or longitudinal data, both phrases are used. When you read about panel data or longitudinal data, there are two typical types of data sets. There are data sets where the sample size is large but the number of time periods very small. For example, we might survey 1,000 individuals and survey them again a year later, and then see how their opinions changed or their circumstances changed. So that is a large and small t type of sample. And when econometricians talk about panel data, this is actually what they have more often in mind, because they think of labor economics. In political science, we quite often have much smaller n, for example, all countries in the world, but much longer time periods. So the time dimension tends to be dominating the size of the sample. And that means that time series conditions become more relevant. And for different estimators and for different kinds of tests, etc., they either have proven consistency as long as t is large enough, or proven consistency as long as n is large enough, or both. So we talked about consistency as when the sample size increases, does the estimate converge to the population value? And these proofs of consistency can either think of t becoming infinitely large or n becoming infinitely large, or both. In terms of fixed effects, it's really very similar to a multi-level model. In multi-level model we were talking about groups of observations, and then some variables that are related to the group and some variables that are related to the individual. You can think of classes and then pupils. Here we think of these time series as a group. So if we have 10 countries over 20 years, then we can think of this as 10 groups of observations, each with 20 different time observations. And so when we talk about fixed effects, we are typically, not always, we are typically talking about having a dummy variable for each of the 10 units in the model. Or since you always have to leave one out, 9 of the 10 units. So fixed effects will then remove all the between unit variation, and then the main estimation is starting to focus on the within unit variation. So how do these time series correlate to each other? So another way of thinking of that is controlling for things like culture or history or path dependence maybe. So you control for features of the units that are not really part of your model. If you are interested in between unit variation or you are interested in variables, independent variables that do not vary over time, for example many institutional variables, then fixed effects are going to cause problems. So unit fixed effects cannot be combined with variables that are constant over time or nearly constant over time. Also, fixed effects take up a lot of degrees of freedom. So if you have a small t and a large n, fixed effects will create problems. Fixed effects only really work if t is sufficiently large. So you have enough information within each unit. Since you are removing all between unit variation, you're only focusing on within unit variation, you better have some within unit variation left. Finally, unit fixed effects make it somewhat difficult to make predictions outside of your sample, because we don't have an average estimate. And that is the same as we said with random versus fixed effects in multi-level models. Now, we typically have fixed effects for units, where we capture things like culture and institutional context and so forth. Sometimes we are more concerned with common shocks, things that happen in the whole world at once, that might change our variables, but that have nothing to do with the within unit variation or developments. So we can also have time fixed effects, dummy variables for each time period. They take away the common shocks in time so that we can focus on what is unique in terms of the movement in a particular time period in a particular unit. If in the literature you see the phrase unbalanced panel, this refers to having different numbers of time periods for each unit, or different numbers of units in each time period. So it's not a perfectly balanced sample. The math then becomes very complicated. So all the equations have to be written quite differently, but the underlying statistics actually work fine. So it is not something to really worry about. It is something to worry about when you want to demonstrate that your estimator works or your algorithm works. But when you are an applied researcher, you have less to worry about. And just like we can use fixed effects for countries, we can also use random effects, especially useful when n is larger or when t is smaller. Then it becomes much more helpful to have random effects. The idea otherwise is the same. Everything that I said in the multi-level class about testing random versus fixed effects using Hausmann, or testing an f-test with all the fixed effects to see if the fixed effects contribute at all, and so forth, they all apply to panel data analysis. So everything that was said about random and fixed effects applies here. Now when we just run OLS, or when we run OLS with fixed effects, we are basically assuming that the error term is the same for all units over all time periods. The variance of the error term should be constant. So the way we estimate our OLS, you will remember that when we figure out the standard errors, we make use of the fact that the expected value of the variance-covariance matrix of the errors is sigma squared times the identity matrix. So a matrix with zeros off the diagonal and ones on the diagonal. Sorry, with a constant on the diagonal, with sigma squared on the diagonal. In panel data, this is often not a very appropriate assumption. So we can actually assume in many cases that probably the error variance is going to be different between different units. So that would be called panel heteroscedasticity. And we also might expect that errors will vary between time periods, but similarly across units. Contemporaneously correlated errors. So Beck and Katz in 1995 proposed an estimator to address this called panel-corrected standard errors. In econometrics, this is not too commonly applied. It addresses some of the concerns we have with errors in panel data, but probably much less than, for example, a proper dynamic model does. But in political science, most reviewers of articles will expect that you use this. So it is very commonly applied, or at least to investigate whether it matters or not. The approach is very similar to what we discussed about wide robust standard errors when we discussed heteroscedasticity in the class on diagnostics. There we discussed how we could estimate the variance of the residuals of the errors by looking at the residuals and the head matrix. With panel-corrected standard errors, we have a somewhat more constrained version of that, where we have estimated variances but for each unit over all time periods, not for each individual observation. So it's a bit more constrained and therefore more efficient. We get somewhat smaller standard errors than with wide robust standard errors because we have a bit stronger assumptions about what the structure is of the error term. So in a normal case, the variance covariance matrix of the errors looks like the omega on this slide, which is the zeros of the diagonal and sigma squared on the diagonal. With wide robust variance covariance matrix, we have individual estimated variances for each item on the diagonal, so for each observation. And then we have different versions, HCC 0, 1, 2, 3, and so forth. For panel corrected standard errors, we have fewer individual sigma squares to estimate. You'll see that there's a lot of the same ones here. It's like sigma squared 1, 2 and 2, 1. You see them many times. But we have on the diagonal, we have for each unit one variance, but that we assume constant over time, but different between units. And off the diagonal here, you have variances that capture the time variance that we expect to be common across all units in one time period, but different between different time periods.